Hello everyone, in today's video we want to discuss maxima and minima of multivariable functions. We will be using dual variable functions for the rest of this unit just because dual variable functions allow us to use an analog in space that we can actually visualize, right? Because if I decided to continue this unit with 3 variable functions or 4 variable functions, you would not get the intuition that's required to study multivariable calculus at such a fundamental level, because you will not get the visual analog. Because of course you can't visualize outputs of 3-dimensional functions or inputs or outputs of 4-dimensional functions in an intuitive way. So because we can use 3D space to model 2 variable functions, we will be spending most of our time discussing 2 variable functions. But note that everything that I say, similar to pretty much everything we've covered so far in the course, can be generalized to functions of higher order or of higher dimension. So I would like to dive into the topic of maxima and minima, which is really kind of a capstone of what we have done in Unit 3. And another capstone will, of course, be the Lagrange constraint optimization that we'll discuss in later videos. Let's get started with some maxima and minima. Here's a definition for you. If f of x and y has a local minimum or a local maximum at a point a, comma, b, then the partial derivative with respect to x of a, comma, b is going to be equal to the partial derivative with respect to y at a, comma, b, which will be equal to 0. So what is this saying? This is essentially saying I have some sort of maybe elliptic paraboloid. We love using the elliptic paraboloid as our examples because it is quite easy to draw. There's our elliptic paraboloid. Draw maybe a cross section or something. There we go. Looks all right. Right, there is our elliptic paraboloid. Now let's say I've got this point, which is of course our local maximum. If I take a derivative with respect to x here, I'm going to get 0 because our tangent plane will be flat at that point. And additionally, if I have a y derivative that's equal to 0 as well, then that means that we're going to have a maximum, because just saying that my x derivative is equal to 0 doesn't really do much for me, because if I say that my partial derivative with respect to x is 0, well, that's all well and good, but my partial derivative with respect to y or with respect to any other direction could be real valued, and that would mean that, of course, it isn't a maximum, it's just a point on my function. So if we can establish that the orthogonal, or the perpendicular derivatives, so for partial x of AB and partial y of AB are equal to 0, then we can definitively say that we have a local maximum or minimum. So note that we require 2 partial derivatives to be equal to 0. Normally in single variable calculus, we only require the one derivative to be equal to 0, obviously a horizontal tangent, but now we need a horizontal tangent plane, right? So we need to make sure that both derivatives are equal to 0, and that will be enough for a valid proof. Now let's try an example. This is a fairly easy concept, but we just want to make sure that we get it down. So I'd like us to find the extrema of f of xy equals x squared plus y squared minus 2x minus 6y plus 14. Okay, so what we're going to do here is we're going to take our partial derivative with respect to x and set it equal to 0. So if I take the partial derivative of f of x and y with respect to x, I get 2x minus 2. Set that equal to 0, and I get x equals 1. If I do the same for partial f, partial y, I get 2y minus 6. Setting that equal to 0, I get y equals 3. So this means that our candidate point where our partial derivatives are equal to 0 is f of 1 and 3. So if I solve for f of 1 and 3, I will get 4. Okay, so we found our extrema value, and we've also found its value for the function, but we don't really know exactly what that is. Now, to realize if this is a maximum or a minimum, usually we would do something along the lines of an increasing or decreasing test in single variable calculus, but in multivariable calculus we need to learn a little bit more about our function and what our function actually is. So if I look at our function f of x and y, looks like I can complete the square here. So if I complete the square of f of x and y, I get f of x and y equals x minus 1 squared plus y minus 3 squared plus 4, which is, of course, we will recognize the equation for a parabolic, or a paraboloid, an elliptic paraboloid. I don't know why I keep getting all these quadratic surfaces messed up. Anyways, but if I look at my equation now, we can look and see that these quantities here, since they're squared, they need to be greater than 0. So we can establish that f of x and y needs to be greater or equal to 4. And well, our established extrema value was 4. So this means that we've found an absolute minimum. So we can see what this looks like on the graph. It's hard to see kind of with this 3D space. Maybe I should put in some videos showing this rotating or something. Anyways, here's our minimum point. You can see it's at point ordered pair 1, 3, 4. All right. So that is an introduction to finding extrema of functions and determining what they actually are. In the next video, I would like to discuss the second derivative test. Don't worry if this stuff seems a little bit complicated. We have a lot more to cover. So we will discuss that in the next video, and we will see you then. Thanks for watching. Bye.